Yeah, here we go. We're going to try to write the exponential model in the form p0 equals p0 times e to the kt. And anytime you're given the 0 point, your p0 is free. So all we really have to do is hunt down the k value. Again, the k value is referred to as the constant of proportionality, but that's the term they use in calculus. In this book, it's actually referred to as the continuous growth rate. So if we can answer number 1, we've actually got number 2 done here. We're going to start by just saying p of t is 100 times e to the kt. And then, because my goal is to solve for k, I'm just going to take my second data point and plug that in to the equation I'm working with. So right now, my second data point is that the p of t value is 200, and that's got to be 100 times e to the 5k. What do I have to do to solve for k? Greg, what's the first thing you would do? Divide by 100. That would leave me with 2 equals e to the 5k. Now what? Take the natural log. Well, what is the natural log of e to the 5k? So I'm one step away. How do I solve for k? Divide by 5. Turns out that k is the natural log of 2 divided by 5. As a decimal, let's take a look. Natural log of 2 divided by 5 turns out to be 0.138629. So as a percentage, what we're saying here is that the growth rate, the continuous growth rate, is simply 13.8629%. All right. Please, oops. Let's go back. So I've got k, and the answer to part B, the continuous growth rate, 13 point, I forget what it was, 8629%. Now that's the continuous growth rate. All right, so here is my function then. P of t is p0, oops, p0 was 100, times e to the natural log of 2 times 1/5 times t. That's what's really happening there. I can show you a whole bunch of quick algebra tricks, but I can actually save you a little work here too. We're just going to say P of t is, tell me about e to the natural log of 2. That's 2. Turns out to be 100 times 2, and then the 1/5 times t is still your exponent. So that's still sitting up here. It becomes the t over 5. So if you look at your instructions, write an exponential curve in the form p0. We have the exact value of k. That was natural log of 2 divided by 5. And now we've actually completed part C, converted to the form P of t is p0 times some constant to the t over n That's not too bad. Okay, next part says, now convert that to P of t is p0 times 1 plus r to the t. This is a little bit more interesting. If I take a good look at this, it turns out that P of t is 100 times 2 to the 1/5 to the t power. 100 times 2 to the 1/5 to the t. Let's take a look at this number. 2 to the 0.2 power is 1.14869. So it becomes P of t is 100 times 1 plus 0.4869 to the t. Yes. Yes, I did. I had 1.4869, so I just broke it up into 1 plus that R value. Okay. I have a question in my head right now, and I don't know the answer to it. I don't want anybody to ask me, so I'm a little nervous about it. So let's not answer question 6 just yet. Let's leave that part out. Hey, let me go back to the original data points for a minute. Scroll up to that. If you want to change 100 into 200, what do you multiply it by? 2. And in this problem, how many units of time did that take? 5? 2. That is not a coincidence. Not a coincidence that this is a 2 and this is a 5. Not in any way at all. All right, let's go to the next one. That's out of order. Let's go to the next one. We want to write our equation. P of t is P0 times e to the kt power. And I already know P0. What is the initial value here? 25. So we're going to start with P of t is 25, and then we're going to go with e to the kt. Now, if my goal is to find k, I simply use the second data point to eliminate the remaining variables in my equation. So this becomes 675 is equal to 25e to the kt. What's that? Good catch. To the 3k. Now my goal is to get k alone. What's the first thing I should do? Grace, what is 675 divided by 25? 27 is equal to e to the 3k. So when I bring a natural log in, I'm going to have the natural log of 27 is the natural log of e to the 3k, which simply turns out to be 3k. Therefore, by division, k turns out to be the natural log of 27 divided by 3. Yes? Yes. Yeah, you can, and I recommend that, but I'm gonna ask you a question before I do that. If you want to change 25 into 675, what would you multiply it by? 27? That 27? And how many units of time did it take in this problem? It took 3. You see how easy it is to predict the value of k? It's a division problem and a subtraction problem. You know, when you did linear equations, if I asked you for the slope between these two lines, you would have said y minus y over x minus x. Now, to find the k value, which is the equivalent of slope in a linear equation, you're doing y divided by y, plugging that into a natural log, and then x minus x as the denominator. So it's a lot like slope. Difference is the slope of the line is constant. This is a constant, but in an exponential curve, the slope along the curve changes. Okay, but I liked your point. What you said is, let's take this natural log 27 and call it 3 natural log 3 over 3, and we end up with just k being the natural log of 3. The significance of that is, if you study this chart, what it's really telling me is that the y-coordinates are tripling with every unit of time. If I were to make a full table on this thing, here's what we'd see. Here's time, here's the amount present at any given time. At time 0 we had 25, correct? This tells me, this natural log of 3 tells me we're tripling every unit of time. So when I get to 1, this goes to 75. When I get to 2, this becomes 225. And when I get to 3, this becomes 675. So the K turns out to be fairly easy to predict just by examining the data points. Now all that other work is just algebra once you have K. Finding the other, finding the growth rate and things like that is just busy work. Let's do one where we're diminishing, where we're decreasing exponentially, and you'll see that it's the exact same process. So I'm skipping down to the table where we've got 0, 100 as our initial point and 225 as our second data point. So we're going to start out right away with the amount present at any given time is 100 times e to the kt. And when I substitute in that second data point, I end up with 25 is 100 e to the 2k. Algebraically, how do I start this process? Divide by 100. That leaves me with 1/4 is e to the 2k. What's next? Take the natural log of each side, which leaves me with e to the 2, which leaves me with plain old 2k over here. Finally, if I divide both sides by 2, I end up with k is the natural log of 1/4 all divided by 2. Now, if you wanted to change 100 into 25, what would you multiply it by? Say again? 4. And in this problem, how many units of time did that take? 2. Again, these two numbers aren't random. They are, by design, going to show up there. So I've created this equation. P of t is 100 times e to the natural log of 1/4 times 1/2 times t. I'm just treating this divided by 2 as multiplication by 1/2. And then I just clean this up a little bit, and I have P of t is 100 times 1/4 to the t over 2. And that tells me what's really happening here. The y-coordinates are being quartered every 2 units of time. The y-coordinates are being multiplied by 1/4 every time 2 units of time goes by. Now, the next thing I can do is I could say this is really P of t is 100 times 1/4 to the 1/2 all to the t power. Give me 1/4 to the 1/2 power. What is it? A half. It's 1/2 to the t. Now, if you go back and you look at this table of values, what this tells me is I'm cutting the y-coordinates in half every time the time unit goes up by 1. Well, let's look at our table again. P of t. Where did we start? 0, 100? According to this, it gets cut in half every time I increase by 1. So when I go to a half, this becomes 50. And when I go to 2, that goes to 25. And when I go to 3, it's going to end up at 12.5. And of course, I could go one step further with this and say this is actually 100 times 1 plus negative 0.5 to the t, and I can see that the actual growth rate here is negative 50%. Yeah, plus negative 0.5. All right, so now if you have questions about yesterday's, wait a minute, before we do that, let's take a look at the back side of this thing. I'll help you get started on this. A puppy weighs 2 pounds at birth and 3.5 pounds 2 months later. If the weight of the puppy during the first 6 months is increasing exponentially, how much will the puppy weigh when it's 3 months old? If I'm going to answer this question, what I need to do is hunt down the 2 data points that are given. So we'll say, all right, I've got a time and a weight. What are the 2 data points they gave me? 0, 2, and 2 months later, yep, 3.5 pounds. Let's go to the next one. Population in Sweden in 1997 was 8.9 million. 2020, the population is projected to be 9.5 million. Population is assumed to be exponential. Find the population model for Sweden, letting time 0 represent 1997. So my initial population is 8.9 million. What's the second data point? 23 and 9.5. Now what you'll notice is there's a slight difference here in the types of numbers we're working with. In all the first page examples, I chose the numbers cleverly, not cleverly, to be nice numbers. You know, 100 became 25. That was an easy fix. So let me show you a really interesting piece of algebra that once you see it, you'll be like, oh, that's really simple. If I want to change 8.9 into 9.5, what would I multiply it by? 9.5 over 8.9. This is that number I'm looking for. And in this problem then, what you'll find out is that the k value turns out to be the natural log of 9.5 over 8.9, all divided by 3. Darn right I would. I tell you what, as you go through this, you'll know this little trick for finding k, and that's great. So why didn't I just show you that in the first place? Because when you see this again next spring, because it's the last thing we study in calculus, right before the AP exam, that little trick for finding k, that's going to be gone. You're not going to remember it then. Then you'll need the process. And at least I can say at that time, here's the process, and it's not completely new to you. Like, oh yeah, I remember that from last year. Problem 3, can you find the 2 data points? It's a little harder to do. How many grams were initially present? Now it says here that the half-life of this plutonium is 24,360 years. How much is going to be left after 24,360 years? 5 grams. So that'll help you find K. And then the question is, how long will it take for this number on the right to become 1? Morphine in your bloodstream has a half-life of 3 hours. By what percent will the morphine decrease in 1 day? All right, so at time 0, that's when you're taking the injection. What percentage of it is in your bloodstream? 100%. If the half-life is 3 hours in your bloodstream, what is that second data point? 350. Once you have those two data points, find K, and now you've got your equation. New car purchased for $25,000. 2 years later, the book value is $18,000. The depreciation is considered exponential. What's the value of the car after 5 years? Well, I need the equation that predicts the value. We'll call it the time value equation. What's my initial value? 1,000. And my second data point? 2. I think this is the last one, isn't it? 6. 4 months after it stopped advertising, the company noticed that its sales have dropped from 100,000 units per month to 80,000 units per month. What are the two data points? Oh, they're calling it N, I'm sorry. At time 0, how many units are being sold per month? Four months later, how many units are being sold per month? 4 months later, we're down to 80,000 units. How many units can the company expect to sell after 2 months? So we're looking for a value in here. Okay, so I think having seen that, you might spot yesterday's homework as being a little simpler than initially presented. Let's go back and talk about any of those you want to right now. Go ahead. Number 11. A piece of charcoal is found to contain 30% of the carbon that it originally had. When did the tree from which the charcoal came from die use 5,700 years as the half-life of carbon-14? So we're talking about percentages here. When that tree was alive, it was full of carbon. But now, because the half-life of that carbon is 5,700 years, after 5,700 years, it's going to have only 50% of its carbon remaining. So we'll go with P of T is 100 times E to the KT. And when I plug in that second data value, we're going to come up with 50 is 100 E to the 5,700K. Do the division, we're going to get 1/2 is E to the 5,700K. Pull in your logarithm, and we're going to end up with the natural log of 1/2 is 5,700K. The K value in this equation is the natural log of 0.5 divided by 5,700, which I think might have been predictable, since if I want to change 100 into 50, I'd multiply it by 0.5, and in this problem it took 5,700 units of time to accomplish. Okay, so here we go. P of T is 100 E to the natural log of 0.5 times 1 over 5,700 times the time, simplifies as the amount present at any given time is 100 times 0.5 to the T over 5,700. Now if you look at the handout I gave you a couple days ago with the half-life formula on it, you'll see that it's always 100. This number is always 1/2, and the number under the T is always the length of the half-life. So as I've been mentioning as we've studied this, all of those equations on that page are the same equation. The half-life one is simply a special case of the exponential growth model. All right, now let's go back up and answer their question. Using the graphing utility, graph the relation between the percentage of carbon-14 and time. They're just saying, draw this graph. Use the intersect, determine the time that elapses until the half-life, until half of the carbon-14 remains, and verify your answer. Did we answer part A or not? When did the tree from when? Okay, so now we're down to 30%, correct? So let's solve this for 30%. 30 is 100 times 0.5 to the t over 5,700. We're going to solve this both graphically and algebraically. So, put here, y equals 100 times 0.5 raised to the x divided by 5,700. And down here we're going to go with 30. You want to know where these intersect? Now it takes 5,700 years to get to 50%, and after another 5,700 years we'll be down to 25%. I'm only trying to get as low as 30%, so for my window, my x-coordinates are time. I'm just going to go out to 15,000 years. That is going to be sufficient. And my y-coordinates are the percentages. I don't have to go any higher than 100. And I can draw this graph. This is the decreasing exponential that tells you what percentage of the carbon-14 is going to be remaining at any given time. And if I intersect these, turns out that it's 9,900.7039 years since that tree has died. However, here's what I can do. I'm better at this algebraically than I am on the calculator, and so are you. It doesn't take long. If I want to solve this for t, what's the first thing to do? This becomes 0.3 equals 0.5 to the t over 5,700. Now what? What's going to happen on the right? This t over 5,700 is going to become a t right here and a 5,700 right there. My goal is to get t alone. What do I have to do? So 5,700 ln 0.3 divided by ln 0.5. Let's go to home screen. Now we said the value by intersection was like this. 57 5,700 ln 0.3 divided by ln 0.5. Not even a hint of an error there. And I didn't have to go find that window. And the algebra wasn't tremendously hard. Best case scenario, I do both, because now I'm very confident that I do. All right, is there another problem from yesterday's homework that you want to discuss? 21? All right. After the release of radioactive material in the atmosphere from a nuclear power plant, 1986, the hay in Australia was contaminated by iodine-131. Half-life 8 days. If it's safe to feed the hay to the cows when that percentage gets down to 10%, how long did the farmers need to wait? So here's what we have. We've got a substance, iodine-131, and it's got a half-life of 3 days. So somehow this iodine ended up in Australia? Austria. Well, on the first day, 100% of it was there. What percentage of it was there after 8 days? 50%. And this question is saying, how long until we can get that down to 10%? Because after 10%, it's going to have decayed away enough that we can feed this hay to the cows. 100 e to the kt. Plug in the second data point, we get 50 is 100 e to the 8k. Divide both sides by 100, I get 0.5 is e to the 8k. Bring in a logarithm. The k value turns out to be the natural log of 0.5 divided by 8, what we would have predicted based on these points. E to the natural log of 0.5 times 1/8 times t, and simplified gives me p of t is 100 times 0.5 t over 8. And then the question asks, how long will it take before this mess on the left becomes 10%? What's the first thing you're going to do? 0.1 is 0.5 to the t over 8. Next up. Why did you bring that natural log in? Bring the exponent to the front. What do I have to do to get t alone?
Divide by
The natural log of 0.1 over the natural log of 0.5 times 8 is equal to t. And what's happening after just a couple of examples, you start to be able to visualize where the numbers are going to be. It doesn't take long. You'll get to the point where you don't even have to write this stuff down anymore. You'll just know where the numbers end up in the final solution. So this is the exact value of the solution, and then we can punch that in. 8 ln 1 over ln 0.5. It'll take about 26.57 days to get to 10%. Because you're going to be some hungry cows if you don't feed them any hay for 26 days. All right, certainly that's enough math for today.